the speakers talked about many things about HPC. I give some overview in the given amount of time. Good afternoon, everybody. I just give a glimpse overview of the how applications have been solved in India on supercomputers, especially CDAC, and what are the challenges which we are facing and how we are overcoming these challenges one by one. So, since long time we have been involved in making large-scale supercomputers that's called Param series, where we solve many of the applications. One of the latest mission which you have seen is Param Yuva, is Param Yuva 2. It's a hard work of 300 to 400 members and solving many applications in weather, sesame data processing, and material science, and computational physics, and mathematics and libraries. See, so today we are living with two kind of paradigms. One is high performance computing. The second one is high throughput computing. In high performance computing, you are required to use more than 1 lakh, 2 lakh processors, 1 million, 2 million processors to solve your problem much faster. High throughput, more than 1 billion jobs you need to process in given amount of time, which you are coming across the Facebook and Google. So both require a huge amount of computing power, huge amount of storage. Then how do you really model these problems? How do you really solve? What kind of hardware and system software, mathematical libraries, everything is required. That's what we. That means what? For any large problem, we need to focus more on how do you really partition data and how do you map this data onto the more than 1 million, 2 million processes, and how the synchronization works, how the communication across many processes take place, and how you can process more than 1 million jobs on such systems. So one way when we build supercomputers like Param series, the other way we also have to address all the challenges from the application perspective, from the management perspective, from running the entire system. Like we have been involved in developing such kind of system from the year 8000 to 2014. Now one of our latest system is Param Yuva 2. It has more than 1 million processors. It's come under the half petaflop range. And now we are building onto the new systems under the National Supercomputing Mission. Let's see. And we also have another facility called Bioinformatics Research Facility, BRAF. The BRAF has got specialized cluster for solving all bioinformatics problems. Many of the softwares like Amber, Gromos, BLAST, FASTA, and many other large-scale sequence analysis database engines are available, highly tuned. Many bioinformatics users, biology users, they use this kind of systems. So these are the systems which we provide to the end users. Then what kind of libraries we do, how we really accelerate the computing, how do we really solve large-scale applications, these are all challenges. So there are more than 100 scientists working on the hardware technologies, software technologies, and there are more than 100 members working on application modeling. These are the areas which we focus to provide the end users, especially application users in the country, a large supercomputing facility at the doorstep. So now we also started using many accelerators. My earlier speakers talked about the GPU computing and cloud computing. We use many accelerators. We have our own indigenous recon full computing accelerators, FPGAs are there. So CDAC is full-fledged large-scale distributed computing facilities with the accelerators capabilities also there. And we also solve many kind of applications that I will see you. One of the latest system which we have built is that Param Shavak. Complete system software, complete management tools, complete applications are available at one box. With this Param Shavak, it can be made easily available to the many engineering colleges. More than 60 engineering colleges in India are having this Param Shavak system, which can be used to many applications. This is one of the latest system which we have been built using many of the open source software as well as the open technologies. That means if you really see all the supercomputers, they have more than 1 million systems. Each system is having more than 8 to 16 processors. They join by different kind of networks. Then where do you really invest time to model application and solve the problems actually? One of the good examples is that you look for performance or scalability, or you look for highly compute, or you need to have a huge amount of storage for IO processing, or you have a huge amount of memory to process your applications. That means you need to have a hardware and software highly integrated in a single system, make it available to the application users. So these are the issues. Now if you see application trends, what you really see is that large scale data come out of the weather simulation, where my earlier speakers conveyed. This large scale amount of data is growing every half an hour it grows, and then the data is in the range of terabytes. How do you partition the data? How do you map onto the processors which you have, and how do you find the solution for this problem? This is one of the difficulty which we need to address. For that we need to do the how you partition the data, how do you partition the computation, how do you partition the input data, how do you map these computations onto the processors, and how do you synchronize, and how do you do the storage handling. All these things are come under the system software and hardware, which we are closely working to provide the large scale solutions actually. The next one is that if you really see some of the models which my colleagues also talked, due to lack of time, I am skipping something. And what you really see is that large scale structural mechanics, large scale fluid structure interaction, how do you really solve these problems? And how do you partition such data onto the 1 million processors? Then how do you do computing? This is also another area where many of the scientists today, they invest more time on application modeling using mathematical libraries, and how do you really design the algorithm to solve on the supercomputers. It's another growing area which is real. And other areas which we really seen is that large scale bioinformatics application, where my colleagues talked about the molecular dynamics, where Dr. Guptaji talked about the Das talked about the molecular dynamics. What we really see is femtosecond simulation you have to do. That means 10 power minus 23 time step you need to compute. That means you require more accurate solution, you require good algorithm to exploit all the processors of the supercomputer to solve. So these are the areas where scientists at CDAC, they interact with the hardware people, system software people, and tune the application to get the better turnaround time and throughput actually. The another application which we have been involved in recently is that large scale data which is coming under the internet traffic among the email exchange, small amount of data exchange through the WhatsApp, or large amount of video images exchange through the Facebook. All this data is also we need to solve on the supercomputer. Here we need to use the operations research, linear programming and optimization, and develop new libraries to see that how we can able to work out the end-to-end solution for the given user. Here more than 1 million, 10 million messages keep going, and you require a high-speed network, that is you require a low latency, high bandwidth kind of network, and you have more than 500,000 video streaming happens, and you require in a busy cities like in India, where more than 1 million, 2 million video frames we need to process in real time to find out the face recognition or the extract some information about the objects actually. This all looks like you require very good mathematical libraries, linear programming techniques, and you also require high-speed computer to solve this kind of problems. Now other problems is that, as my colleagues talked, how about this detection of observations in the astrophysics, more than billion stars? How do you model such kind of large scale astrophysics problems in the graph theory, and how do you partition the graph, and how do you do the computation, how do you do the force computation, how do you do the long range, short range interactions? All these problems are again, one way you have large amount of data, other side you have the more number of processors, and how do you intelligently develop algorithm focusing on partitioning and computation performing synchronization. These are the issues where future areas are there, where you require to invest more amount of time on computation and the design algorithm and accessing that large amount of data and processing. All these things are equivalent to the solving present era of applications using supercomputers actually. The second problem which my colleagues also talked about, the drug design, where we talk about the protein-protein interactions, where atoms at the micro scale are much below, they interact, where we need to talk about the how do you model such kind of protein-protein interactions to use graph theory, how do you do the force fields, how do you do the long range interactions, short range interactions, a billion molecule kind of simulation we need to do. One of the interesting areas is that how do you do query processing in large data, how do you partition the data, how do you process the query, how do you do mining, how do you do the community detection in this kind of applications. These are another areas where we need to do most of the work. That means what? We have one way, hardware and software will be there, other way you have the algorithm design, everything is also equally important. So these are the things which we need to focus. The another area which is that video, video summarization and video. In a busy places, you would like to find out the face recognition and object recognition. For this to do, you have the more than 1 million frames for a video is going to come, and you need to process in real time. For that, you require to use GPU processors, and you require to compute all this data in real time. So this is a combination of high performance computing and high throughput computing, and you require a large amount of computing processors, what we call high performance clusters we require actually. So this is also another area which many of the application people are now coming of the new challenges and new algorithm design. So what you really see is that how the video frame section. Now to do this kind of video processing, either you apply the typical distributed computing paradigms like message passing or Hadoop MapReduce. These are now growing in last 2 to 3 years, where the huge amount of video data sets you can process using Hadoop MapReduce under the big data framework, which is also becoming more and more attention. As the day progresses, the data sets are increasing. Designing algorithms using mathematical libraries is going to be major challenge in the future, where CDAC is making lot of efforts in this direction. And another area which we really working on is that how do you do large scale image processing? If you really see the some of the avalanches and some of the large scale images, you have more than 1 million images, and all these images you need to find out spatially some objects in each image. That is what called spatial searching. The spatial data searching, what we call spatial geographical information system, or the spatial data processing. How do you do it really? So this is another area which is grown, because here the data set is in the form of images. Most of the images may be very small. You have maybe 10 million images. All 10 million images, you can concatenate them as a single largest image, that is of around maybe 1 terabyte. And how do you process on the supercomputers? This is also another growing area. The other one which my colleagues also talk, which I am skipping, how protein-protein structure interaction goes, what kind of computational speed required, how do you design algorithms, how do you design the libraries for this, how protein-protein interactions can be modeled using graph theory, and how large graph of 1 billion can be partitioned on the partition, how we can map onto the supercomputers. This is also another area which CDAC is making lot of progress. What kind of programming paradigm we need to use. So these are the new areas which have come up in last 2 to 3 years, and we have been working very seriously how we can really scale these applications on 1 million to 10 million processor of the supercomputers. And digital agriculture is another new area which has come. You know, I think in India we have agriculture is the major source of research activity. Today we want to do the maximum yield, and today we would like to have the crop growth. Then this is also a linear programming problem. This linear programming problem is for every acre, if you really maximize yield, minimize the cost, and if you want to handle the shortage of water, if you want to handle the monsoons, if you want to handle the cyclones, everything, the entire problem is very complex. For every acre of land, if you do the optimization problem, you require maybe a few minutes to compute on the supercomputers. But the entire country, if you really want to do, you require more than 100 million processor supercomputers. So this is also another area where it impacts the society, and you can also have the crop growth at the district level and hectare level. All these things are also possible. Here, the combination of hardware, software, algorithm, libraries, and linear optimization research, linear programming, operational research, and modeling the digital agriculture problem all are issues actually. So this is also another new area which we have been coming out with the various solutions. Now if you really see what we do at CDAC is that we develop our own networks, we develop our own switches, we use the off-the-shelf commodity processors and provide a complete solution to optimize the given application and provide solution to the end users. So the most importantly, what I covered about the application challenges and then hardware, software, but what kind of programming paradigm do we really use? We have many programming paradigms. Every system level we need to use appropriate programming paradigm, and across the clusters we need to use different kind of programming paradigm. When the data is very used, we need to use Hadoop MapReduce kind of programming paradigm. So with this, I am just trying to convey about the activities. The last one is that we have Grid Garuda, where all the supercomputers in India
which CDAC is involved. They are all conducted by the National Knowledge Network (NKN), which is called Grid Garuda project, which have been they are operational since last 10 years. So all the supercomputers, when they are connected, every user can access the supercomputers available across the network so that he can solve much more problems. So thank you very much for giving this opportunity.